Hello, welcome to SECOORA's webinar series, Coastal Observing in Your Community. Thank you for sharing your virtual lunch hour with us. My name is Abby Wakely, SECOORA's Communications Director, and I will be facilitating and moderating the webinar. SECOORA is hosting this webinar series to discuss, highlight, and raise awareness about coastal ocean observing activities in the Southeast U.S. and beyond. SECOORA is the regional coastal ocean observing system for North Carolina, South Carolina, Georgia, and Florida. We are one of 11 that make up the NOAA-led U.S. Integrated Ocean Observing System, also known as USIUS. Our mission is to sustain and promote observations that help keep you safe. This is a quick snapshot of the technology we support to accomplish our mission. Below are 3 pieces of SECOORA news I quickly wanted to share with you. SECOORA is hosting lightning talks with 8 of our funded principal investigators on Monday, June 29th. This is an invitation to please join us. There's more information on the SECOORA website, secoora.org. I also wanted to highlight that SECOORA is membership-based. Members guide all of our activities, and membership dues allow us to invest in ocean observations, research, and student opportunities. Please consider joining SECOORA. And then lastly, do you have a project you want to share on our webinar series? Email me. We have spots to fill in the fall, and we normally get about 100 people tuning in at a time. All right, let's get to the reason you're all here, the webinar. All participants will be in listen-only mode. You are encouraged to type questions for the presenter or technical questions for me in the bottom right chat for the Q&A box. I will respond to them directly or post the questions to our presenter after his presentation. We are recording this webinar today and will be posting the recording on the SECOORA website. We are very excited to welcome Dr. Matt McCarthy from Oak Ridge National Laboratory. He will be presenting coastal 3D high-resolution maps for floods, wetlands, and biodiversity. Dr. Matt McCarthy is a research scientist at Oak Ridge National Laboratory, home of the world's fastest supercomputer. He earned his PhD working in remote sensing of coastal environments at the University of South Florida. He grew up in Gainesville, Florida, fishing and boating on both the Atlantic and Gulf Coast. Dr. McCarthy now conducts research using advanced satellite image data to map and monitor those coasts for changes caused by a variety of drivers. Thank you all so much for joining us. Dr. McCarthy, I'm going to go ahead and stop sharing my screen and promote you to presenter so you can share yours.
Sure, thank you, Abby.
And it is passing now.
All right, it should be coming up. Just let me know if you can see the slides and if you can hear me clearly.
I can see the slides and I can hear you. Perfect.
Perfect. Okay, well, thank you for that introduction. Good afternoon, everyone. Thank you for tuning in. As Abby mentioned, I recently began working at Oak Ridge National Laboratory, but before that, I was working as a postdoc at the University of South Florida, where I conducted several large-scale mapping projects with high-resolution satellite imagery, some of which are ongoing, and all of which I am still involved in. So I'll be talking today about those projects, which require the collaboration of the folks you see listed below, from USF, Texas A&M, and Rookery Bay National Estuarine Research Reserve. Now, this work is part of MBON, the Marine Biodiversity Observation Network, as a networking entity that helps develop best practices for coastal and marine biological observations, and is working with IUS to integrate biology into the observing system. This work is also relevant to the biological essential ocean variables, or EOVs, defined by the Global Ocean Observing System, which includes IUS by addressing coastal EOVs and including mangrove cover. The population of the US is forecasted to grow by approximately 125 million by 2050, according to the US Census Bureau. Yet only about 50%, 50% of the built environment needed to accommodate this population exists today. Further, vehicle miles traveled typically grow 3 to 5 times faster than population. Coastal counties, where population typically grows faster relative to the rest of the nation, require visionary land and urban planning to mitigate losses due to flooding. The primary motivation of the project is to help ensure the rapidly growing communities and industry occupying low-lying coastal areas of the southern US will be protected and developed in a sustainable manner by planning based on knowledge, conservation, and wise use of sensitive lands. The geographic scope of the project is the coastal floodplain from Texas to Florida, including the east coast of Florida, And the mission is to update topographic and land cover maps for this region and improve the capacity of regional planners, resource managers, and emergency responders to assess flood risk and to plan for conservation of sensitive habitats. We hope that our high-resolution 3D land cover maps will complement the land cover maps updated periodically by the Coastal Change Analysis Program, or CCAP, which I'll be coming back to in a bit, of NOAA's Digital Coast Program. Our maps will be compatible with traditional land cover classification maps, but at 200 to 900 times the spatial resolution of the official CCAP product. They also will complement the high-resolution CCAP maps planned based on historical airborne imagery, and all products will be distributed openly. The increased spatial resolution will also help improve first-order estimates of biodiversity throughout the region. So the research questions that we're addressing with this project are primarily those listed below. We're interested in identifying the types and extent of different wetland and other land cover classes, as well as their geomorphology, composition, and vulnerability at both local and regional scales. We want to understand the relationship between topography and land cover across scales of meters, identify which areas are particularly prone to flooding across the study region, and ask what are the major changes observed in land cover pre and post severe storms, and specifically the storms we've had recently, Hurricanes Harvey, Irma, and Michael. As you probably know, the Gulf was the landfall site of Hurricanes Harvey, Irma, and Michael in 2017 and 2018 as categories 3, 4, and 5 storms that caused hundreds of billions of dollars in damage and resulted in lives. Oops, somehow I switched ahead. And the loss of lives of over 100 lives. Hurricane Michael was the strongest hurricane in the Florida Panhandle and only the second known Category 5 landfall in the northern Gulf of Mexico. With warming waters and a changing climate, we can expect more of these powerful storms to pose serious threats to our coasts. Additionally, along the eastern U.S. seaboard, nuisance flooding is increasingly frequent as well. These areas are indicators of what other coastal communities as sea level rise continues. Indeed, some of the worst flooding in Texas is occurring in areas experiencing subsidence due to natural and human causes, including groundwater or oil and gas extraction. In fact, between 1900 and 2000, some areas have seen up to 3 meters of subsidence, and these areas then flood first and often hold floodwaters longer. So to address our research questions, we create large-scale, high-resolution, 3-dimensional maps using 2-meter spatial resolution, WorldView 2 and WorldView 3 imagery, with Lidar point cloud-based digital elevation models as well. WorldView satellites circle imagery every day with a repeat acquisition of on Earth's surface almost daily. Lidar data are typically collected as needed and as resources are available. As you can see on the right, we have a DEM generated from Lidar point clouds of Texas, and I'll be coming back to more examples of those in a bit. This work is primarily funded by NSF's Hub-Spoke Big Data program. We received $1 million for a 3-year project to map land cover for the entire U.S. Gulf of Mexico coast, from the coast to about 50 kilometers inland, with an emphasis on wetlands. The area comprises about 20,000 WorldView 2 and WorldView 3 satellite images at 2-meter spatial resolution. And these are commercial imagery, and typically one has to pay for them, pay for each individual scene. And we've estimated that the number of images required would amount to around $30 million. Now, conducting this kind of large-scale mapping presented a number of problems that we had to address. The first problem was simply in getting the work done in a 3-year time frame, which required us to develop automated methods for mapping all 20,000 images. But with automation comes additional problems, including issues with consistency in maps produced from different images. Now, we approached that problem by using as many standardized pre-processing and mapping algorithms as we could. Many automated methods use thresholds that hard-code arbitrary indices, which is problematic when encountering an image captured from a different time of year or with different sun and satellite angles. So we address that issue by using scene-specific algorithms wherever possible, and I'll mention an example of those later. Now, although we were not specifically working on benthic mapping for this project, we used this opportunity to develop methods to address 2 problems common to coastal water bodies that many of you are probably familiar with. That's sun glint and water column corrections, for which we developed novel algorithms, and I'll talk about those in a little bit as we just published some papers on those. These considerations were worked into a mapping pipeline we developed called SOALCHI, which stands for Spectral and Object-Based Automated Land Cover Classification of High-Resolution Imagery. It uses a combination of Python and MATLAB code that we ran on the USF high-performance computing cluster to improve its efficiency. As an example, when we ran it on the Texas coast with over 2,000 images, we completed what would have taken about 5 years with traditional single image mapping methods in just under 1 week. We're currently 2 years into the 3-year project, and we have finished mapping everything except Florida. Florida is ongoing right now. So I'll talk a bit about the actual workflow and the methods, and then I'll talk about validation and then some applications. Now, the first step in this pipeline is a Python script written by the Polar Geospatial Center, which ingests the raw satellite images, optionally georectifies them, projects to WGS 1984 or any projection we choose, and outputs a geotext. And this typically takes only about 5 to 15 minutes to run depending on the size of the image. The next step is to ingest that intermediate geotiff into a MATLAB script that I wrote, which converts the digital numbers to radians, corrects for atmospheric scattering, and converts to remote sensing reflectance before mapping the image with a decision tree. Preparation for the decision tree includes the derivation of several intermediate products, including object-based maps, like the example seen here, which is used to distinguish soil and developed land cover from water and vegetation. So this object-based map is then used within the decision tree to apply spectral patterns to distinguish between soil and developed land. So in other words, we first distinguish between classes A, B, and C, D, and that will then let us go in and further distinguish between class A and class B. An example of a spectral pattern used to distinguish between classes is shown here in a graph of the average spectral reflectance patterns of upland and wetland vegetation. You can see that they are very similar, and if we were to look at a cluster of many individual patterns, instead of averages, you would see that they overlap quite a bit and vary depending on time of year and sun angles. So to distinguish between these two classes and accurately map wetland vegetation, I derived an algorithm that sums 3 bands together for every vegetation pixel in the image, computes the average, and later maps wetland vegetation as those pixels whose sum of those 3 bands is less than the scene average. And this pattern holds because wetland leaves tend to have higher concentrations of water, which brings down those reflectance values. So in other words, we created a scene-specific algorithm that does not rely on hard-coded indices, but rather uses the information from the scene to define what the threshold between upland and wetland should be. Now, I'll briefly mention that within this automated workflow is a series of algorithms I developed for automating the mapping of water quality in bathymetry, although this element of the project is not actually in the initial proposed work. First, I developed a way to automate the deglinting of water, which is a fairly standard process when applied manually by identifying visually areas of glinted and unglinted water, but that I have automated with a new algorithm for identifying glint and distinguishing it from optically deep water. So I'll show some examples of that in a moment.
Hey, Matt, you still there? I think we might have lost Matt. Give us a second. Thanks for bearing with us. I think we're all used to technical difficulties now.
Process with a moving window filter to remove pixelation and smooth the final output as shown here, where the image on the left is the initial output that is smoothed to the image on the right. Blue represents water, red is fringing mangrove, green is grass, and black is soil. The result then is a more accurate representation of what we see on the ground rather than the initial pixelated version.
Hey, Matt.
Yes.
We lost you on that last slide. It's like you cut out. Could you repeat, go back one more slide.
Sure. I'm trying to. This slide?
One more back. Yes. I don't know if we saw that one, but you cut out right when you said you were going to show examples.
Oh, okay. Sorry about that.
No worries. I'm going to go back on mute.
Okay. Right, so I was discussing the deglinting process and how I'll show some examples of that in a moment. So once we have the deglinted water body, we can then use modified water quality algorithms to determine, including how much chlorophyll there is, again at 2-meter resolution. After all that preparation, we run the decision tree mapper itself to deglint water, estimate water quality, and we can even now map bathymetry and output a bathymetric map. To do this, I derived additional algorithms from the literature, applied to the WorldView satellite sensor in an automated way to map depth down to about 15 meters in clear water. So I'll show another example of that in a moment. After the decision tree creates an initial lane cover map, it is automatically post-processed with a moving window filter to remove pixelation and smooth the final output as shown here, where the image on the left is the initial output that is smoothed to the image on the right. Blue represents water, red is fringing mangrove, green is grass, and black is soil. The result then is a more accurate representation of what we see on the ground in the image on the right, as opposed to the initial pixelated version that we see on the left. The final step in the pipeline is to then mosaic these 20,000 images together into a seamless product. We first divided the region into 13 smaller subsets to make the batch processing and mosaicing more manageable. The final products will be delivered by state, probably. Stitching the images together is usually a very time-consuming step and one that is often done in software like ArcGIS. But my attempts to do so often crash the software because of the magnitude of data being merged. So we developed a method using Python and the GDAL library to mosaic the images on the supercomputer, which reduced processing time and never crashed. I should also mention that although we use a supercomputer to do most of this processing, all of it can be done on a standard desktop or laptop computer. We simply use the supercomputer because it is essentially stringing together many hundreds or thousands of computers so that you can process more than one image at a time. So I want to go through some examples now. This first example is of the deglinting algorithm, where you can see on the left a raw WorldView 2 image of a coastal area, and it's full of glint because there's wave action that's reflecting the sunlight off of the water. The image on the right is the deglinted product, where you can now see substantial differences between the shallow water and the deep water. And you can even pick out the differences in the benthic habitats, where you can see areas of patch reefs, seagrass, and hard bottom or sandy soil. Here's a second example of the deglinting algorithm, where on the left we have the raw image with some wave action over a shallow coral reef. In the image on the right now, we can clearly distinguish between the deep water in the top left corner and the rest of the scene. And we can see a much better view of the coral reef itself and distinguish it from the other benthic habitats. Here's an example of the bathymetric mapping that we've been doing. The image on the right is a combination of 3 WorldView 2 images stitched together, mapped for bathymetry. And this is of Key West, Florida. The image on the left is a reference map from NOAA's topographic Lidar DEM, which we used to validate the image on the right and found that the root mean square error is about 0.64 meters. And typically anything better than 1 meter RMSE is considered accurate for satellite-based bathymetry estimates. So here's a result from the Texas mapping. You can see the raw output on the left that's mosaic together. Now at this point, we've completed the Gulf-wide mapping except for Florida, which is currently running. Our mosaic map is on the left with a matching digital elevation model on the right, derived from LiDAR data at the same 2-meter resolution. I'm showing Texas here just because even at this zoom, it's difficult to see the details. But we have the same digital elevation model and maps for the entire region. We zoom in and compare our map on the right with the NOAA Coastal Change Analysis Program map on the left. We can see that the 2-meter resolution data allows us to identify much more detail than the 30-meter NOAA map. We can distinguish major roads, side streets, buildings, parks, front yards, and backyards with the higher resolution data. In this example of a more developed area, the NOAA map considers the entire region to be a single class, whereas our map picks out those vital details. The next step for this project, after completing Florida, is to combine these land cover maps with the elevation models, which can be used to derive water flow based on elevation gradients. By combining that elevation-derived water flow with land cover, we can then model how rainfall or storm surge flooding would move across permeable and impervious surfaces to help improve flood risk prediction. So that's where we are now, 2 years into the 3-year project. Now I'd like to take the rest of the time to show some examples of how we've already used these maps for applied coastal research. Applications include guidance for sustainable coastal development, evaluating flood hazards, and ultimately pursuing further expanded mapping by using the input data sets here as training data to conduct machine learning-based mapping if that proves to be more efficient or accurate. In other words, we're sort of looking ahead to the future to make sure that these methods can be improved upon and continued to continue monitoring the coast over time. One element of the end of the project that I won't get into today is in structure for motion, or SFM mapping. One of our teammates, Mel Rogers, is using extremely high resolution drone imagery to derive 3D topography at centimeter level, like seen in the example figure shown here. What you're looking at is a beach and the vehicle that Mel used to get to the study area shown in a 3D image. So we're conducting this detailed work at select sites around the Gulf for an even higher resolution product. Now, our next step was to evaluate the SOALCHI method we developed against existing robust methods in the rapidly developing field of machine learning. This validation work was published earlier this year and aimed to map habitats in Rookery Bay, Southwest Florida, using 3 different methods and comparing the pros and cons of each. The algorithms were our SOALCHI method, which I'll also refer to as the decision tree, the support vector machine, and neural network algorithms. We used a single WorldView 2 image because it was collected at the same time that we were conducting a 3-month field survey of the same area to get ground validation points, with which we could perform a robust accuracy assessment on the resulting map of each method. We used 714 field points to conduct the accuracy assessment. We divided that into 2 batches, and because the support vector machine and neural networks require training data, we used the first half as training. We did not use any training for the SOALCHI as it does not require training data, and we used the second batch of 300 plus points to do the accuracy assessment on each of the 3 maps. The November 2018 image was captured 1 year after Hurricane Irma made landfall here, providing a challenge for the algorithms to accurately identify both healthy and degraded natural habitats. Here are the results, both in tabular and figure form. On the right, you can see a zoomed in area of the study area of Rookery Bay, showing our SOALCHI or decision tree method on the top, compared with the maps from the neural network and support vector machine below it. And on the left, you have the accuracy assessment results. And from these results, we can see that each of these methods has a very similar overall accuracy, ranging from 83 to 85%. But when you dig into the actual class-specific results, you'll see substantial differences. And those differences were what we pulled out in this paper to describe the pros and cons. So essentially what we found is that the decision tree method is the fastest, as well as the only automated method that we used here, and it produced the best upland versus mangrove accuracy. However, it was the least accurate at identifying damaged mangrove. Support vector machine algorithm was the most accurate at identifying damaged mangrove, but it was also the slowest and required manual training, as did the neural network. Neural network was the most accurate overall, and it was the most accurate at identifying healthy mangrove. So we placed these pros and cons in the context of future mapping and clarified that each of these pros and cons should be considered depending on what the goals of the project will be. So after that accuracy assessment and algorithm validation product, we revised the damaged mangrove algorithm, which performed relatively poorly in that example, to improve its accuracy and applied it for a time series analysis of natural disaster monitoring. Now, we were already mapping imagery from 2010 to 2018 for the NSF project, and so we could use it to evaluate changes that occurred along the coast, like quantifying the damage caused by Hurricane Irma on Rookery Bay mangroves in Southwest Florida, and observing how they recovered a year after Hurricane Irma had passed through. This was a separate project funded by the National Estuarine Research Reserve to map the reserve and distinguish between damaged versus healthy mangrove following Irma, and evaluate where mangroves died or recovered 1 year after the hurricane. The existing study area map is from 2010 and took them about 2 years to complete with manual and digitization and a lengthy field survey. This project addressed a specific management need, which was to identify the location, extent, and time frame of coastal wetland degradation in Rookery Bay. Our goals were to determine chronic versus acute drivers of change and to help managers determine how to mitigate loss, understand recovery, and improve resiliency. The project goals were to map land and aquatic habitats for the years 2010, 13, 16, 17, and 18, detect change location and extent, attribute those changes, and share the information with regional resource managers through facilitated meetings and mapping products. We used the high-resolution WorldView 2 and WorldView 3 satellite imagery. We also used Landsat data for this project so we can compare the results with the different spatial resolutions. We intended to incorporate Lidar data, and we also conducted field surveys to do the ground truthing that I mentioned earlier. With our SOALCHI method, we were able to map 91 images from 2010 to 2018 in under 4 hours, whereas again, the existing map took about 2 years. Doing so required us to develop a new algorithm that I mentioned to identify damaged mangroves specifically, which is difficult because of the fact that it is both a mixed class with partially defoliated canopies, broken branches and trunks, and possibly debris or overwash on the ground beneath the exposed canopy, and because it is by definition ephemeral and will eventually convert to something else, either recovering or dying and being replaced. So here are the results of the accuracy assessment after we revised the algorithm and ran it on the WorldView November 2018 image. We found that the overall accuracy was 82%, and our degraded mangrove class was substantially improved over the initial algorithm results. I've got a series of slides showing now the comparison of the WorldView map on the left with the Landsat of the same time period map on the right. And you'll be able to see here that the maps generally agree, but there are some substantial differences, especially in how they identify healthy versus damaged mangrove. And you'll also see on some of these maps, we've called them marsh vegetation as opposed to degraded mangrove. We kind of went back and forth on what we should call these, and there's a lot of debate within the field. So I apologize for the difference, but you'll see that they're either called marsh or degraded mangroves. Here's a view of 3 months following Hurricane Irma. And you can see again that the bright green represents that marsh or degraded mangrove, and they generally agree between the WorldView and Landsat images. And I include this map because one, it's from about 5 to 6 months after Irma from both of the images, but you can also see one of the weaknesses of the WorldView satellites, which is that it does not always have the coverage necessary to map the entire desired study area. Landsat images have coarser resolution, but a much larger geographic footprint. So a single image can cover a very large area, whereas with WorldView, you need more images, and sometimes those images don't exist to cover the area that you want. So that's sort of a pro and con to be considered as well. So now I want to focus then on the results from just the WorldView maps, where we were able to accuracy assess and quantify the results. Results indicate that most of the reserve before Hurricane Irma, as you see on the left, was covered in thick, healthy mangrove forests, shown in bright red. But 3 months after the hurricane, as seen on the right in bright green, much of that mangrove forest was damaged. 1 year later, in November 2018, a lot of the mangroves had recovered, but some of the areas had further declined and appeared to have died. If we zoom in on one of these specific areas, you'll see what I mean. The top image is from 3 months post-Irma, again from WorldView. Please disregard the blotches in the top right. Those are cloud cover, and they were not included in the quantification later. But you'll see in that top image that much of the area there is degraded mangrove caused by Hurricane Irma, shown in bright green. But then 5 months post Irma, in the image on the bottom for the same area, you'll see that a lot of that bright green initial area changed to bright red, indicating that the damaged mangrove had recovered. However, some of those areas changed from green to yellow or orange, indicating sand or mud, suggesting that the satellite is able to peer through any potentially remaining branches and see the soil below, which we interpret as indicating at this point in time, 5 months later, that that mangrove had actually died off as opposed to remaining degraded or recovering. So we quantified that change and found that over 7 square kilometers had converted from mangrove to marsh or damaged mangrove forest. 1.6 square kilometers had converted to bare soil, suggesting that they had died completely. And total mangrove decline amounted to over 10 square kilometers, representing about 10% of the study area. This paper was just published a few weeks ago as an invited feature article in remote sensing, so you can dig into the details a bit more if you'd like to. Now, we also wanted to identify the drivers of change. So I've zoomed into a specific area here that we visited in the field because it was so unusual. This area used to be a black mangrove stand, but it actually degraded or even died before Hurricane Irma came through. So in order to understand it, we went out and visited the field, as had been done before by previous researchers, and we found that most of the area remained inundated, and it appeared to be caused by rising sea level that would flood the area, but then the water would remain there, evaporate, and increase the salinity of the soil. Or at least that's sort of our working hypothesis for some of these specific areas that were degraded before Irma came through. There's also a paper published by Radabal et al. From FWRI in 2019 that studied the effects of marl overwash and found that it had likely starved mangroves, resulting in delayed mortality, such that 2 to 3 months after Irma, about 11% of their measured mangroves had died, whereas 9 months after Irma, 20% had died. So there was this delayed mortality event that they attributed to the overwash that had been dumped onto the forest floor beneath the mangrove stands by Hurricane Irma's storm surge. Furthermore, we evaluated local sea level rise by looking at the Naples monthly mean sea level tide gauge from 1966 to 2017. We looked at this as a potential driver of some of the changes that we had seen independent of Irma. Now for this time period, which is the length of the record, the rate of sea level rise was about 3 millimeters per year, which agrees with the global average. However, if we look at shorter time periods more recently, we find that from 2000 to 2017, there was an acceleration in sea level rise to about 7 millimeters per year. And from 2010 to 2017, that it further increased to about 14 millimeters per year. On top of that, we found that the 2010 to 2017 lowest mean sea level was about 40% higher than the long-term average. Now, it's important to consider that there are periodic fluctuations in sea level that typically occur around 18 years or so in this region of the Gulf, and those must be considered in the long-term evaluation of sea level rise. However, when we're looking at relatively short period effects of sea level rise on the mangrove area, this information should be considered as it is clearly influencing the mortality of mangroves in some of these island areas. There is some good news, however. The Radabal et al. 2019 paper found that 3 to 9 months post-Irma, there is about 60% canopy cover, which indicates some recovery of mangroves, but it also allowed for more sunlight to reach seedlings, which we saw here in a field survey during January of 2019. So there is certainly substantial indication that mangroves in at least some parts of Rookery Bay are coming back. And that's another reason that this kind of work needs to continue in the future so that we have both a baseline monitoring now, and so that monitoring will continue into the future and evaluate how these changes occur, especially if there are more hazards or accelerating sea level rise or additional storms that impact the area. So I'll wrap up by indicating that the next steps in the project, of course, are to complete the Florida mapping. That's ongoing right now, and it should be done very soon. The next step then will be to conduct flood risk mapping. Jim Jabot from Texas A&M is leading the Lidar digital elevation model derivation effort. Those products, as I mentioned, will be combined with the land cover maps for flood risk mapping. And then in the end, we will be disseminating the results. SECOORA has kindly offered to possibly disseminate the results for us. We're exploring Digital Coast, or really anyone else who would be able to disseminate these for us. We want them to be freely available and easily accessed for anybody. Now, of course, SECOORA includes areas not mentioned here. And so for future work, we're hoping to expand this to the Eastern Seaboard. And so if anyone on this call has any ideas for how we might do that, or how we might be able to partner together for future collaborations or proposal, please feel free to mention that or contact me. My email address is located here. I also wanted to point out that the funding for these projects was provided by NASA, NSF, NOAA, the Neuroscience Collaborative, which sponsored the work in Rookery Bay, and NOAA IUS. And the data that we received was provided by Digital Globe and the Polar Geospatial Center. So with that, I think I left ample time for us to have a discussion. I'd be happy to answer any questions you may have. So I'll turn it back over to you, Abby.
Great, thanks, Matt. If you want to keep sharing your screen in case anybody, you need to reference a slide, we do have some questions coming in. Folks can type questions in the chat box or the Q&A box, and I'll ask Matt. And we had one come in already, and will the completed mapping include the Florida Keys?
Yes, the Florida Keys are included in the work, so they should be in the final maps.
Great, thanks. And then what is the resolution?
The spatial resolution is 2 meters by 2 meters, or about 4 square meters per pixel. The temporal resolution, which means how frequently are the images mapped, that varies quite a bit. We limited the images that we requested to images that had less than 20% cloud cover. So we eliminated a lot of images that we otherwise might have included because we can't see through cloud cover. But we have images for the entire study region from 2010 to 2018, and we're probably going to be making different versions of the final product, where we have perhaps one version where we have all of the images together mapped into a single land cover map. We might have another map then that is from the early years, 2010 to 2014, for example, and sort of a post map from 2015 to 2018. So we're hoping to have several products, but again, they're all going to be at 2 meter spatial resolution and cover that 2010 to 2018 time period.
Great, thanks, Matt. We had another question come in. Is the WorldView imagery free?
That's a good question. So it is commercially owned. So typically WorldView imagery is not free. However, USF and a number of other government, academic, and other institutions have access for free to all of the imagery through a NextView license. In order to get the license, I know you have to apply for it. I don't have a link here, but I think if you just to Google NextView, one word, license, you could find the information about how you might go about applying for it. And I'm not sure what the current restrictions or requirements are in order to get that imagery. But I would also say that if you're interested in doing this kind of work, there are 2 considerations. 1, access to the imagery, and 2, having the data storage and processing capabilities to be able to work with it, because these data sets are rather large. And so I would highly recommend anybody interested in kind of delving into this work to consider partnering with USF or another entity like us to partner and kind of leverage our resources to make the work a bit easier and more feasible.
Great, thanks, Matt. We're having quite a few questions come in. What are the classifications used for the Gulf?
Yeah, so we have 10 classes right now. They are soil, developed land, what we're calling senesced vegetation or dead vegetation, which is often just senesced during winter, scrub shrub, wetland marsh, upland vegetation, upland forest, upland grass, forested wetland, and cloud cover, I think is what we're working with right now.
Great, thanks. And we have another question. I assume these various automated mapping methods would work for international locations. If so, are there any plans to expand this work internationally?
Yes, actually, we are very interested in expanding the work internationally as well as completing the rest of the US coast. The work is ideally suited to expand internationally because the work does not, the algorithms that we've included do not require training data. So in other words, we don't need to go to the coast of South America, Brazil, for example, collect ground field data to train an algorithm to do the work. We can simply ingest the images, order the images, ingest them, and conduct the mapping. And so what we'd really like to do is to partner with some groups who would like to do that kind of work, especially if they have some kind of field data that we can use to validate the work and make sure it's accurate for different areas of the world, so that we ensure that the algorithms we created for the Gulf region will indeed be relevant to mapping different areas of the world. So definitely, if you're interested in that kind of work, please reach out.
Great, thanks, Matt. And you might have touched on this earlier, but what habitat type / land cover class scheme was the data resolved to, and / or what scheme is it anticipated to be provided in?
Yeah, so our goal was to try and match the CCAP, Coastal Change Analysis Program format. Now, CCAP has 21 to 22 or so classes, including ice and snow, so we didn't actually try to capture all of them. In fact, we've been communicating over the past year with Nate Harold and the CCAP program to try and ensure that our products would meet their standards, especially as they endeavor to create high-resolution maps themselves using aerial photographs. So from what I understand, the CCAP program is trying to create these 1-meter maps with different methods, but for, I believe, 6 classes is the last that I heard. So we took those 6 classes and we expanded on them to further parse out, for example, forested wetland from forested vegetation. So in other words, we didn't pursue one of the more detailed existing classification schemes. What we wanted to do is try and make these accessible to anyone using CCAP products because CCAP is so widely used already, but then just build off of what they're doing with their high resolution maps and build out those thematic classes in a little bit more detail.
Great, thanks, Matt. And then are there any publications out now relating to your work?
Yes, there are 2 that I referenced in the presentation. Let's see. Yeah, Abby, what's the best way to, should I send them to you, send them in links, or should I just sort of read out the names of them?
Yeah, you can send them in links, and then if we have your permission, we'll also be posting a PDF of your presentation along with the recording on the website.
Okay, that'd be great. That's probably the best way to do it. But yeah, we just in the last, let's see, 2 months, 2 or 3 months, we had 2 publications. One published the validation work that we did comparing the machine learning methods with our SOALCHI method, and the other was the description in greater detail than I discussed today of the work that we did in Rookery Bay. So I'll send those to Jennifer or Abby, and she can send them out.
Great, thank you. And then we had one more question. You can keep the questions going. We have till 1 o'clock. Do you think the processing time will increase a lot if you convert the MATLAB code to Python, R, or Octave, if the conversion is even possible?
Yes, great question. We're actually in the process right now of converting everything to Python so that it will be run in one seamless single language open source method. That way we can avoid using the licensing of MATLAB and run it all a little bit easier. As far as speed, we expect it to be pretty similar. I don't think we've finished yet. I kind of transferred that over to our partner Tyler Murray at USF, and I don't think he's finished the actual conversion yet. So I can't speak for certain to what the speed will be like, but I would expect it to be very similar. And to give you an idea, when we run it on the supercomputer and we can run multiple images at a time, the imaging the mapping typically takes around per image. And you can do that on a laptop or a desktop. And so it would take 1 hour per image, but if we run them multiple images at a time on the supercomputer, for example, if we run 2 images at the same time, then the average processing time is cut down to a half hour, and so forth. So as far as speed, that's not really even an issue right now, but yeah, we're always looking to increase the processing efficiency, and hopefully Python will help us do that to some extent.
Great, thanks. All right, any more questions? We still have 15 minutes. You can type them in the chat box or the Q&A box. And just give it one more minute. If you have any questions, go ahead and type them in.
And thank you for taking your lunch hour to talk to me, or to listen to me.
Yeah, thank you guys. All right, so Matt, I am not seeing any more questions come in. So, oh, I have one more. Would the code be made available as part of articles or on a repository?
Yes, right now the code is on our private GitHub repository. It will be made freely available when the project finishes, probably even before it finishes within the next few months. What's happening right now is that I've kind of transferred my duties over at USF to a couple other people who are trying to further develop the algorithms. So for example, I mentioned some algorithms having to do with deglinting and water column work and bathymetry. And so as those algorithms are further developed, they will kind of be polished and put into the GitHub repository and be made freely available as soon as those are kind of cleaned up. And we're hoping that we'll have both the initial Python script, the MATLAB script, and hopefully we'll also have the MATLAB converted to Python script available, again, freely available to anyone who wants to use it.
Great, thank you. People are thanking you for code sharing.
Oh, sure, absolutely, it's important.
One more question. Have you compared the Florida data with the high resolution LiDAR data that Florida International University has done some time ago?
I have not done that, but I know our partner Jim Jabot, who's on the NSF project, who's leading the actual LiDAR derivation work. I believe he and his group are collecting all available LiDAR that is publicly available and pursuing some non-public acquisitions as well. And so I imagine they have it. If there's a more specific question I could answer, please shoot me an email. I could even put you in touch with Jim Jabot if that would be helpful. I'd be happy to do that.
Great, thanks. And then another question has come in. Thinking about circulation modeling for the bathymetry, what is the typical depth that you can get good data?
Yeah, that depends entirely really on how clear the water is. But the existing publications of sort of manual methods to map bathymetry with WorldView imagery suggest that you could get down to 30 meters. We have been cutting it off at about 12 to 15 meters because at that depth, in the areas that we've been studying, which are not perfect ideal conditions, they're typically off the coast of Florida where you might get turbidity or chlorophyll or CDUM or otherwise. Beyond 12 to 15 meters, it can get a bit dicey and the accuracies decrease. So I think if we were going to put out a product freely, it would probably be cut off at 12 meters, but we'd also be happy to further expand this work, perhaps with more detailed training data to help us validate the algorithms and develop them further. If anyone was interested in delving into that work to deeper depths in possibly isolating target imagery that's really kind of perfect for that kind of deep depth work.
Great, thanks, Matt. And you guys can see Matt's email at the top. I can also include it in the email if you all do want to collaborate and discuss more. Another question has come in. Have you included DEMs with imagery for classifications?
Yeah, that's actually one of the next steps that we're going to pursue. One of the problems we had with the classification was in distinguishing between soil and developed land. But what we found is that we could use the LiDAR DEMs to accurately identify buildings and create kind of a building mask to distinguish between soil and buildings to help improve that classification. So that's one way that we want to do it next. And we're also considering using those DEMs to help improve the classification of upland versus wetland habitats. We already have some pretty good spectral algorithms to do so, but because we have all this fantastic data, we're going to try and explore ways that we can use the DEMs as much as possible. And if there are any more ideas, again, please feel free to reach out and we'd be happy to work on that or collaborate more.
Thanks, Matt. And we got time for a couple more questions if anyone wants to type them in. I'm not seeing any right now. I know from SECOORA, when you guys get the code available in Florida done, we'd be more than happy to host a news story and share that information through our networks.
Oh, good. Yeah, please. That'd be wonderful.
All right, so I'm not seeing any more questions. I'll just give it one more minute. All right, we're getting lots of thank yous for the great presentation. So thank you, Matt. I'm gonna take over really quickly and just share my screen. I want to thank you all so much, as Matt said before, sharing your lunch hour with us. It was a great presentation. And Matt, thank you for the fabulous presentation. We'll be sure to get the recording up, and if we have permission from Matt, post a PDF of the presentation, and then also include the publication links. And here you will find a recording on SECOORA.org/webinar series, and it will be posted by the end of the week. And thank you guys again. And Matt, thanks again. This was a great presentation.
My pleasure. Thanks, Abby, and thanks to SECOORA.